I'll go back. I have to be back around.
Can you hear me now? Is there any improvement? Ivan is there. There seems to be no audio.
Hi, Ivan.
Now it sounds right. Okay. Let's see. I don't think it's that direct because there is a buffer, so it will take like a minute or so before he actually hears.
Should be fine. You will be sitting somewhere close?
Yeah, sitting around.
I mean, if he writes a text message or something.
Yeah, he texts me on my phone.
Yeah, can you tell him?
I just did.
You did. Everything is perfectly set up. Amazing. Very good. Well.
Let's see.
You still watch my friend?
Okay, let me know if something doesn't work.
When I was there for 2 weeks, you kind of get like, then you get back here, something. Yeah.
Vengono così senza effetto,
Did you like?
Yeah. No, really? We like the 90s, but it's all I'm so sorry. I'm so sorry. That's his name. Name throughout the whole apologizing. No, I didn't. This thing doesn't focus. It's out of focus. He says this seems to be unclear. I think it's just poor resolution.
Okay, I've been going
I'm not sitting at this desk. How long is the delay? I wonder. Sì. This is better.
Which is really but there was also
How do you know? Is it better now? There we go.
Please be seated. It is a great honor and pleasure for me on the behalf of the University of Bergen and the Faculty of Mathematics and Natural Sciences to welcome you all to this doctoral defense ceremony for Mattia Natali. He was admitted to the PhD program at the Faculty of Mathematics and Natural Sciences in February 2011, and he has been supervised by Daniel Mattel, his main supervisor, and co-supervisor Ivan Viola, both from the Department of Informatics. Mattia Natali has been a PhD candidate at the Department of Informatics. In May this year, Mattia Natali submitted the thesis Sketch Modeling and Conceptual Visualization of Geomorphological Processes for Interactive Scientific Communication for being evaluated for the degree of Philosophia Doctor at the University of Bergen. The following committee was appointed to evaluate the thesis: research scientist Dr. André Brodtkorb from SINTEF in Oslo, and Professor Dr. Bernd Fröhlich, Bauhaus Universität Weimar in Germany, and Professor Dr. Pinar Hegnes from the Department of Informatics. The committee found the thesis worthy of being defended, and the following opponents were appointed: Professor Bernd Fröhlich and research scientist André Brodtkorb. Members of the audience will have the opportunity to ask questions and present comments after the examination of the two opponents have been completed. The defense now starts with the candidate Mattia Natali presenting his thesis. I have the honor to call upon the candidate to take the floor.
Thank you very much for the introduction. Good morning, everyone. And today I will defend my thesis that is with title Sketch-Based Modeling and Conceptual Visualization for Geomorphological Processes for Interactive Scientific Communication. I started my studies, PhD studies, in 2011, and it was a part of a project called GeoIllustrator. And I did my studies in the visualization group here in Bergen, University of Bergen. The thesis is based on three main papers. I will call them A, B, and C during the presentation and also in the dissertation. So the objective of the project, that was called GeoIllustrator, Methods and Tools for Illustrative Visualization of Earth Models, was to reproduce these illustrative models, as you can see here in the figure. This is one model taken from a textbook, And this is a reproduction made by our tool, just to show that these models try to represent processes that take place on the Earth. So the problem statement is that there is this importance of communicating abstract ideas. This is already true in geological illustration that you find in textbooks, or the geological illustration that are used to communicate between experts. And they express and explain processes involved in the subsurface. They have to be simple and quick, especially when you want to model it, to draw the model. And in our case, we haven't used any data, so the models are created from scratch, and we don't acquire data from measurements from the field. And we try to avoid the geometric constraints as much as possible, so we use a free-form drawing approach. And the approach is intuitive for non-experts. And here, I thought that the best way to represent the visual thinking procedure and process, I thought it was a good idea to show this illustration, because when you have something in mind, you imagine something, then you want to draw it, to show it to someone else, and then at this point you also see it and decide if this is what you had in mind, or if it's something different. If it's something different, then you can imagine something else and then correct the drawing and proceed in a loop and make this synergy stronger and stronger. And in our case, the drawing part will be replaced by the modeling part, and the seeing part is the visualization part. Those are two examples of geological illustrations. The one at the top, for example, shows a process of a magmatic intrusion. So when the two blocks here of layer goes apart, then there is an intrusion from the mantle of the Earth. And another example is here is an example of fault, where you just have to communicate simply that there is a movement between the two blocks, different rock types. For example, here you have the 3 rock types, and each texture represents a different type of rock. And I've looked into the related work of the computer graphics community, and then I tried to find out what was the state of the art to construct such models. And I found out that mostly these approaches were for the top surface and the terrain modeling part. And if there are some measurements, or there is some data coming for the construction of the model, then there is a process that interpolates this data and builds the model. And every approach has a different representation. For example, here we have an example where they use a approach to reconstruct this surface that I think is the triangulation. And here it's similar to our approach, where they use sketch-based inputs to construct the surface, and here a volumetric representation. And we have noticed that for models that also represented the subsurface, the tool starts to be too complicated, because it's full of details, and it's maybe too much information in the same model. For example, For data-free modeling, so without any measurements, that is our case, we have two main approaches. One is a procedural approach that includes the fractal and the erosion simulation, but this one has a lack of control. In the same way, the geometric approach, code by example, has some lack of control. You can guide the approach by setting as some examples that you recognize as similar to your idea. But the approach that is more similar and more that let more freedom to the user is a sketch-based approach. And here we have an example, but this example has a general approach. It doesn't focus on geological features. This other one is an example of erosion simulation, I think from a volumetric representation. Here there is a parallel between the architecture board and the geology. Because in architecture, we know that if we want to have every detail and everything into the model, we can use such specific software that englobe every information inside the model. But if we want to achieve such a model in a quick way and with only the concept of the model, we can use something like this. So we achieve a conceptual visualization of the model. This is something we are looking for in geology, because such softwares that are geoscientific software specific for the subsurface are too complicated, and we want something that is quick to do and simple. That's why for the motivation, we need a rapid modeling tool in geology, and that is based on the sketching approach. And few methods have been applied to geology, and the illustration has to be interactive, because this allows for inter or cross-disciplinary communication between experts. And the image at the bottom is one of the first examples I have, just showing that with few curves you can get to the model. I will explain the approach in a minute. The target domain is specifically structural geology. Structural geology is the study of three-dimensional distribution of rock units with respect to their deformational histories. And visualization in geology, as I already said, it's used for a discussion between experts or for teaching purposes, or even for industrial strategic decisions. The main or the most studied processes, geological processes, are the folding process and the faulting process. A fold in geology is a deformation of an originally flat layer that has been bent by forces acting in the crust of the earth. While the fault or the faulting process originates when the forces that act on a specific layer are so strong that the rock layer breaks and produce a fracture like this one you can see here. And the common approach for a geologist would be to go on the field, see such a geological event, and then to try to represent it as quick as possible, maybe on a notebook, like a 2D sketch. There's an example here. Or if we want to be more precise, you can also define with this illustrative texture some properties of the rock. In this way, there is he or she can reduce the details in favor of simplicity and rapidity. And then it doesn't have to be to use parameters, but just is for her drawing abilities. So we want to reflect this approach to construct a 3D model. So we fuse the sketching approach to achieve an illustrative geological illustration. And this is done with our method. And the first approach we had is described in paper A, and it's a sketching approach on this that is done on the cross-sectional view of the model. You start looking at the vertical plane, and then you start drawing. For example, if you want, considering just one rock layer, if we want to sketch one rock layer, we just have to sketch two curves, defining the limits of the layer. And then, if we want to apply a texture, we just choose which one, and the texture automatically adapts to the curves. And the surfaces are generated by extrusion of the curves. And in this case, we want to add one fold to the model. Then we just have to define the fold trace and the amount of displacement of the blocks, and then we achieve this. But in this way, with the automatically adaptation, we can convey the folding process. If we want, for example, an erosion, we have to define a different shape for the texture, and this is done by following another sketch, or still defined by the user. This is the blue one. And the pipeline for this approach is that you have these sketches here on top, and then for each sketch you extrude to get the surface in 3D, and two surfaces are put together to create the rock layer. And in this way, when you have more rock layer, you define a layer cake, what is called a layer cake model. And then, if you want, you can apply some texture on the layers. And texture is very important in these illustrations because every texture has a meaning. And when we apply the texture to the rock layer, we have to maintain the meaning of the texture and its expressiveness. And we do it by applying a conformal mapping, what is called a conformal mapping on the model. And conformal mapping, it just means that you preserve the angles, because we are using a triangulation. And when we go from the texture space to the surface space, the angles are preserved. Or there is a functional that is minimized to allow a preservation of the angles as much as possible. And those are some examples of the method. You can see here a fold example, or maybe an intrusion from the mountain, or this one we have seen already with a more non-photorealistic texture. And we compared our results time-wise with an estimate given by an illustrator working with these geological models. And we, for example, for this first example, we can use just 2 minutes, or more or less 2 minutes, and the illustrator would employ a full day to do it. Because the problem is when there is the deformation of the texture around certain points. And similarly, for the other example, there is a time saving for both models. But now we are talking about the static illustration. But we are describing something that is dependent on time. So we want to introduce the variable time into the model. So we started to collaborate with a colleague of mine, and we described a method to create animation of the processes. And this is done in this way. We have the initial configuration and the final configuration of the drawings that represent a situation in time of the geological process. At this point, we interpolate the curves, the corresponding curves in the two configurations, and then we achieve time steps in between. And the curves then are extruded with the approach I described previously, and then we can achieve something like this, that is the animation of the process from the starting point to the final compression. And I have a quick animation for this, showing how it works. You see that the bricks don't have to be too much distorted, otherwise the texture loses its meaning. Okay, but after this approach, we try to introduce fluvial systems into the models. And fluvial systems are important and are studied by geologists because their history is imprinted into the subsurface. And here you see how the river evolves in time. It started here and it started to deposit its sediment here. And then it is important to see how it behaves and how it shaped the underground. And to define such fluvial systems, we have to change a bit our approach, because now we have to sketch from the top. And we decided that we wanted to use, for example, this is a top view of the model, and we wanted to use a grid representation for each layer that is that corresponds to a sketch. In this example, we have an example of a river and an example of the position of a mountain shape deposition. And each sketch corresponds to a grid, and the grid, for each point on the grid, has a value that corresponds to the amount of deposition or erosion. If it's a positive value, then it's deposition. If it's a negative value, it's erosion. And then when we put together in a sequential way all the grids, then we achieve the volumetric visualization at the bottom. And here it is explained for a 2D example. You see here the grid seen from a side view. This flat grid corresponds to a constant, a layer of a constant thickness, like this one. And then, if we want to erode the layer, we have to apply a grid that has this shape, where here we have negative values, and we get the erosion. And we continue in this way. If we want the deposition, we have positive values, and so on, to get to the final visualization.
Yeah.
I can show a video explaining how the approach is done for different for different processes. We start with the constant layers, and then we define a way to deposit material, and this is done with closed curves. If you define a closed curve, then there is a deposition, and if you set the value as negative, then you get an erosion. Here I show how the negative erosion works, and you see that there is erosion. You can see the layers underneath the top surface. And here you can see that with simple sketches you get already complex models. Now it starts with simple examples, but then it will grow. Okay, this is just for closed curve, and in a minute I will show how it works for open curves, because an open curve corresponds to the center line of the river. So I will show with the rivers. The sketch that is done on the top of the model corresponds to the center line of the river, and then the section of the river corresponds to an analytical function defined by us. Then you can change the width and the height of the section of the river. And if you remember in the geological illustration I showed at the beginning, you want to draw an evolution of the river. So to do this, we have to define the initial configuration and the ending configuration, and then there is an interpolation in between that shows you can choose how many rivers you want in between, and then the interpolations start, and you get the evolution of the river. Can go a little bit quicker. And with the cut views, we can show the internal details. Now the final example, just fast forward, where we combine every feature. Yes. Now I can go back to the presentation. Where I show some results. Here to the right we have the model. These models created by our approach, and this is an illustration made by Ture that collaborated with us. He's a geologist, and we show that we could reproduce each of the block here in the illustration. And another example is how a delta deposition behaves. Here I show that I can sketch from the top the shape of the deposition of a river coming from this side. And if we want to communicate different grain sites into the deposition, we can assign a color map to the volume. And then to inspect the internal part of the model, we can use the cutting planes like I showed in the video, or we can also use this view that is called the exploded view to show independently each feature inside the model. And we also provided this called staircase view, where you cut just the layers that you want to remove, or just to reduce the occlusion on the other layers. And this is a temporal cut, where you decide at which time you want to see the geometrical process. At this point, we had support for stratification that is considered as deposition and erosion, and for folding processes, and for Fourier system. What we wanted to introduce is folding processes and compression of layers. For the folds, that we have many cases, and we have always two blocks behaving such that you have pressure from the side, and the pressure, if it's convergent, and you achieve something like here or here, it's called a reverse fold, where the two blocks goes on top of each other. If the forces are diverging, so the two blocks goes in opposite direction, then you have a normal fold, and they slide going away from each other. And for example, if we have a reverse fold like this one, the process or our approach to construct the illustrative representation is this one. We have the start constant layer, and then the user defines the shape of the fold, both on the side and on the top. And then we reconstruct the surface that represents the fold, that is called F. And the surface cuts the grid that is called the top grid T and the bottom grid B in these points. And then we know where the displacement takes place. And the problem with our representation is that when you put this green block layer on top of the orange one without anything, then there is the green layer fall on top of the orange one. To go around this behavior, we have to support the green layer with a transparent lifting wedge that you can see here. When the reverse fold, then you need also a supporting wedge here. But in the final visualization, they are transparent, so you don't notice it, and you can achieve this displacement of the fold in this way. And the approach for the contraction works like this. If you imagine this 1D example with the three layers, H1, H2, and H3, and you want to convey the compression of one of them, for example, the bottom one, then you assign a weight to the layers on top, and the weight is dependent on the height or the amount of the position on top. And then you have a coefficient that depends on the height, and the coefficient is from 0 to 1, so you get the compression. Here I show how it looks like here without compression, here with compression. And you see that the more the position you have, the more compression you get in the layers, in the lower layers. Okay, and the final example, put together the compression and the fold. Here it's without compression and without fold, and here with compaction. You see the difference if I go back and forth, and now with the fold as a final example. Okay, so the methodology, so the method we used is a layer cake model in paper we published to show the internal structure of the illustration. And we use illustrative visualization to show structural geology, and we introduced a novel representation that is the one with every layer corresponds to a height map or grid. And then we propose the rendering algorithm that takes from the representation to the final polymer visualization. And so of 3D single model. And for domain application, we have provided support for stratification, deposition, and erosion, for faulting processes, and then we applied the conformal map for the formed rock layers, and we provided also the texture that is guided by the drawing of the user. And then there is a support for fluid systems with their deposition and the compaction of layers. In the example on the bottom, you see an example of an evolution of a delta deposition, where with the 4 sketches you get the evolution of the deposition that is more visible here. The deposition starts with this feature on top, and then when the sea level goes down, then the river deposits in different places, and then if the sea level comes up, then the deposition. And as a conclusion, I showed the layer cake visualization showing the internal stratigraphy, where we combined 3D sketching tools to achieve geological models. And it is a method that is fast and intuitive for the user. And we introduces tools inside the models. That is something that for other it's not so easy because it depends on the representation you use. And yes, the last slide I showed some references I used during the presentation. As this one I used those references. And thank you very much.
I wish to thank the candidate for the presentation, and I'm asking him to remain on stage, waiting for the examination by the opponents to start. I now have the honor to call upon the first opponent, Professor Bernd Fröhlich.
So yeah, thanks for the presentation. Thanks you for inviting me here, for being on this committee of Mattia. Of course, it's always an honor to be on these committees, and but it's also a duty. And in this case, I can already say that's a pleasurous duty to be on this committee. First of all, I think I should say something about our committee. So since I'm presenting kind of a short version of the report, and so Andre Butkop and myself were on the committee, and you know that Butkop has also a translation to German. It's the same word, and Fröhlich also has a translation, I think, to Norwegian. So we are the listic Butkop team today. Anyways, so let's go into the report. I think here in Norway especially, there's a lot of interest in the oil and gas industry and other parts of the world too, to efficiently locate the precious oil and gas reservoirs. And these techniques, of course, are developed to locate these reservoirs, which has gotten more difficult over time. Models of the complex subsurface structures have to be built, in many cases, little data or just with knowledge about similar regions or adjacent explored subsurface terrain. The modeling and data interpretation process is performed by geologists and geophysicists and involves locating and specifying particular features in the subsurface rock formations, such as horizons, falls, ancient river beds, and other things. The process is laborious and time-consuming and often still performed using 2D drawing programs, which have no or little support for these typical geological scenarios. The challenge is, so, to expedite this process and facilitate the modeling of subsurface structures, the documentation and communication of these imagined subsurface structures. And Matthias' thesis sets out to improve this process by developing and exploring expressive sketching techniques, as we have seen. The thesis is written in English and divided in 2 parts. That seems common here in Norway. So part 1 is introduction, description of the state of the art, an overview of the contributions and results, followed by conclusion and future works. Part 2 contains the 3 scientific papers, and I will just say a few words about the first part. It serves the goal of presenting the context of the published papers, and it does this very well. The extended related work chapter grounds the contribution in the geoscientific domain and in the visualization domain. The overview of the technical contribution and the results of the peer-reviewed paper perfectly connects the related topics, as we just saw in the talk, and nicely shows how the work evolved throughout the thesis. The final conclusion summarizes the solid contribution of this thesis and touch on some avenues for future research. So part 1, well done. Let's come to part 2. So, because these are the papers, and I think they always form the core of the thesis. And the first paper, paper A, is the paper Rapid Visualization of Geological Concepts by Mattia, Ivan Viola, and Daniel Patel. So, as we have seen, we saw there's a rapid sketching tool for illustrative layer cake visualizations developed, and the main idea is you draw on a slice, as we have seen, and this is extruded in 3D. So that's the basic model, but I think the key feature here that made this a very useful tool is really the deformation of the textures, an efficient and easy way to deform the textures that are put on this layer cake model. And this, I'm sure, led to the improvement in the sketching time from a regular 2D tool to what can be achieved with this tool from, say, hours or a day, even to minutes. And I think that's a great improvement, and I think that's a very worthwhile idea in this paper. So the next paper, it's of course it's the strongest and highest rated paper in this thesis, sketch-based modeling and visualization of geological deposition, published in Computers and in the journal Computers and Geosciences by Mattia Natalie, Arne Clausen, and Daniel Patel. I think really a core thesis, because here it really extends upon the ideas of the previous paper. In the previous paper, first paper, we basically have an extrusion depth of slice and something you sketch on a slice. And now we look at the model from the top. It's a completely different view, and I think it's a very great complementary view. So here the user starts by drawing strokes to define river systems, deltas, lakes, mountains, and basins, and the volumetric model is created and visualized using raycasting on the GPU. And the results of this framework have been evaluated with domain experts. And I really like That's how you did that. I mean, first of all, you digged into the geology domain. That's amazing. But also that you used experts from this domain. And it's known that most of the usability issues in such expert reviews that he did, that if you have 5 experts, you can find 75% of the usability issues in your program. That's actually that's known. And so it's fine that you don't have like hundreds of geologists trying the tool. In an expert review, you can already find out that it works well. And they graded the tool with good to very good. So I think it's a great success. The paper contains undoubtedly excellent technical and likely impactful contributions, I think. Otherwise, it would not have been accepted to the Journal of Computers and Geosciences. Clearly illustrates the rapid generation of successive visualizations of various hypotheses concerning the surface structure under investigation. So that's great. And now we have the third paper, paper C. There were some limitations with the model in the second paper, and the third paper actually builds on that and adds the possibilities to express compaction and faults. So it uses sketches on the surface of the back box, and the system automatically uses the shape to create from the sketch either constant thickness layer, river, erosion or deposition, fault. The parameters of the features are then set, the sketch converted into height maps, and multiple layers are superimposed to create a full volume. Finally, compaction is computed to generate the final illustration. We have seen that the results are visualized in several ways, not only as a direct visualization of the model. You have stack-based views, exploded views, and all of them are very useful. And these methods had to be and were implemented on the GPU to make them run in real time, and so they can actually be used as an interactive tool. And what I also like here, again, the results are compared to that professional illustrators, and you have seen in the talk that there are highly similar results, and with a highly interactive tool. And the number of figures that were shown here in the talk, they were created in less than 2 minutes. That's amazing for such complex models. So, let me summarize part 2 of the thesis. The major contribution of Mattas' work are rapid sketching tools for creating illustrative visualizations. The 3 papers contain far too present solid technical contributions in the domain, which clearly advanced state-of-the-art. Particular strength of this work is that it was carried out and evaluated with domain experts. I appreciate, or we appreciate this reform. The presented techniques may lead to a new generation of interactive sketching and illustration tools for the geoscientific domain. The applicability of such tools extends beyond the few use cases explored in the thesis, such as archaeology, geothermal industry, and ore extraction. Further, we can also incorporate sensor data and real-world measurements into the sketching framework, as it is already outlined in the thesis. Mattas presented 3 internationally published peer-reviewed papers as part of the thesis. One of the publications appeared in the renowned Journal of Computers and Geology. This is certainly a great success, since this journal is read by computer science and geology experts. So it's really crossing the boundary. The 2 other publications appeared at respective conferences. 3 further papers, which are not included in the thesis, appeared in very good journals. State-of-the-art report on volume terrains and subsurface geology was presented at the Eurographics 2013 top-tier graphics conference. But here, after this, productivity is very high, as you can see. In 3 years, he published 7 papers. That's really amazing. In total, 7 papers in total, and he was the first author on 6 of them. All his publications are beautifully illustrated and well written, as is the entire thesis. So, this leads to the final verdict from the report. Monday, and I had the pleasure to review this thesis and the papers, and we can say that his work, Matthias' work, is solid research. This is really documented by a number of significant research results, which have been published in good and very good venues. Thus, his work clearly fulfills the requirements for the PhD degree in computer science. So far from the report, well done. And I think had the opportunity to ask some challenging questions after giving the report, and I think that's also a good part of the pleasure here to prepare some questions and challenge an expert on this topic. I mean, I have also some experience in working with the oil and gas industry and with these kinds of models, so we'll see how our experiences and thinking about these topics match. So, let's see. Layer cake models in paper A. You started with a very simple approach to get these models. I mean, an extrusion of a slice and some sketched lines on it. It's not a 3D model. One could say it's maybe a 2.5D model. I thought when I read this, I thought, well, it's a pretty simple model, but it's an excellent start in a thesis, right? You have to get familiar with this topic, and this seems to be a common model. But I was wondering, really, if it's not possible or not easily possible to have multiple of these sketched slices, right? And then consider them like as keyframe animations in depth, and then basically connect them so you get a slightly more complex model. Because you don't find any spot of the Earth where true extrusion happens in that direction, right? So I was just wondering if something like this would be possible, or you could think of making this possible. Slice, another slice, and you would maybe take a sketch on the first one, and then refine the slice, change the sketches on that slice, and then another one and so on. Do you think that's possible, or how could you make this?
If this is possible. The first idea I had to extend our approach was to sketch on the second dimension. Instead of having this cross-section of this, to sketch the second dimension. But in this way, you have also other limitations.
Yeah, it's a tensor product kind of surface. Yeah.
But if you want to maintain the simplicity and the rapidity of the method, then we compare it with the original illustrations, then this method goes the simplest one. But it's true that if you have multiple views, then you can interpolate, and it's not so easy because the details inside can be very, very difficult to achieve. But you can interpolate between different views and get an extrusion that is more a 3D model than 2D.
If you copy a slice, then you would have a correspondence of the lines you already generated, the sketched lines on this slice to this slice. So, and that these correspondences would help you a lot. There's actually an interesting paper from Henrik Fuchs and Kedem and Usselton titled "Optimal Surface Construction from Planar Contours." That's a paper from 1977, I guess, before you were born. But nevertheless, what they did, they used CT images, and they also drew basically like the contours on each slice, and then the contours on the different slices had to be connected. And this is the algorithm that connects the contours on the different slices using some energy minimization technique. So I think something like that could also work for you. I thought just found it interesting that people have thought about connecting slices so many years ago already. Okay, so let's come. I still have a few minutes, I guess. Let's come to the paper B, and the volumetric model here is represented as a set of stacked height fields and visualized using raycasting. I think that's quite an advancement, because now we have more of a true volumetric model compared to the paper A, where you started in your thesis. And the raycasting algorithm accumulates color as it marches through the volume. But it seems like since it's stacked height fields, it seems it's not a true volume rendering, in the sense that the volume can change at every sample point. You're mostly interested in the intersections of the ray with all the height fields along the ray, right? And you use an algorithm to compute these intersections. That's a very, say, simple algorithm that basically probably computes the intersection with the boundary box, and then you have a projection on the xy plane, and then you march along the projection, right? And it seems very similar to relief mapping or parallax mapping that's used on the GPU to render height fields, for example. And in fact, the software code doing this in software, not on the GPU, is probably from the 80s. And I think Sabine Cotillard's PhD thesis was on this topic of rendering height fields, and she did it in the same way, but she didn't use stacked height fields, just similar single value height fields there. And but the question is, with such an approach, is how do you control the sampling rate of the height field? Because the height field has certain resolution, you also need to control the sampling rate so you don't miss any intersections and so on. So how do you control the sampling rate, and how do you compute the actual intersections?
The sampling along the ray it's uniform sampling, and so we don't have to compute the intersection in the height maps. And for each sample along the ray, we check if this point is the Z component is between the height in that XY position of the top layer and the bottom layer. If it is in between, then it has some properties related to that layer. Or and to that point we can assign frequency in the model. So we don't have to get the intersection with the ray we have. For each point that is a uniform sample along the ray, we just have to check if it's inside the ray.
Yes, I see that. But you would just have the intersection with the boundary surface, and the next intersection with the boundary surface. Then we could use the distance and perform the ray integration based on that. Because the material in your volume, as far as I understood, is homogeneous. So you don't need to step along the ray in that setting. Because if your material is homogeneous, right?
Yeah.
But if it's not, then is it homogeneous or isn't it?
Yeah, in our case it is not. And
So,
but the difficult part is to get the section.
oh, to get the intersection, the height field is very simple. If you have a height field, and you have one sample that's below the surface, one sample that's above the surface, you can use binary search to find the intersection very quickly. This is not
We can improve the method and
absolutely. I think
publish something.
yeah. well, that is not possible because my PhD student Christopher Lutz has published a paper in 2011 that is called GPS breakcasting of sections out of 4 height fields. So that's not possible. So it's done. and it can be done. But in fact, if you want to scale this to very large height fields, you would not use equidistant sampling along the way if material is constant inside the layer, because for efficient ray intersection with very large height fields, you would use something like a control acceleration scheme or something like that. And, you also for KD tree type acceleration scheme, because that allows you to quickly find the intersection point, and then but it's interesting if you have multiple height fields, you have to have another structure that deals with the exact height fields and to accelerate that intersection as well. And that can be done, of course, either using a true 3D structure or 2D plus 1D structure. I think there's potentially a proof that. But why I wasn't sure if you use really constant material inside a layer, and the reason why I wasn't sure is that there's one picture where you showed color-coded the different grain sizes in the model. And there I thought, well, if you do that, the property inside a layer seemed to change. How did you model that?
And this is an interpolation within the code. So you have this time in the visualization file.
Sure. But
So the layer
yeah.
as one is homogeneous.
Yes.
Then when we visualize it, we use a function that is called name that apply color map to that layer. So you can choose the color map that you can apply to the layer, and you choose the colors you want to assign to the grain size.
Right, but if the material is homogeneous, I would not know how to use a color map to change the material inside the layer. So
it is interactive with the user.
Okay, so you basically in the layer somehow you have a possibility to assign in the end different material properties in the layer.
Yeah.
It is.
Yeah.
Right, something like that. And then you of course need volume rendering and then sampling stuff. And just if you have such additional features that make it a true volume. Great. Okay. In paper C, in the last paper, you converted the height field representation into a true volumetric representation. I was wondering why did you do that, and is that more efficient for rendering? At least I understood. That's what I understood.
Yeah, it's not a conversion. It's that the layers, instead of having a relative height, we have the height fixed.
Yeah, absolutely. That I understood. But that's like height field still.
Yeah, but we still maintain the height. We don't go to the approximation.
Oh, okay. I think I understood that from the back. Okay, then that's fine. I have one more question here. That in paper A, you start with the nice deformations of your layers, and you keep the textures in a nice shape. And then this seemed to be an important feature for the meteorologists that form layers, and that you have the differently deformed textures on these layers. But in paper B, that's no longer, it doesn't seem to be any more important to have these textures. And in paper C, we added deformations again, which was not possible in paper B. But the textures didn't seem to come back in paper C. Is there any reason?
I guess it's possible to introduce the but we thought that photorealistic rendering aims. We keep the illustrative approach. And but in theory, you can use you can apply either 2D textures or you can apply 3D texture to the entire model.
Exactly.
Yeah.
Right. But see, the textures that are used in paper A, I would not call them photorealistic. I mean, they are symbolic. Symbolics. That's texture that just tries to and so on. They are not photorealistic. And the way you would have to use it is the solid textures or 3D textures, I think. And in my feeling, it was really important to have those textures in paper A, and later it was not so important anymore. But I feel probably important. And if you could have the same ideas from paper A transferred to your model in paper C and have solid textures that are deformed, and you cut into this texture and you see the deformation textures in combination with the compaction that you simulated there. I think there's a lot of potential further to improve this model at this point, to combine basically your contribution from paper A and from paper C into paper D, maybe.
Another way to combine them would be to start from the first approach with the sideways and then build on top of that with the second approach.
That's
then
true.
put the texture.
Yeah, yes, and then that's right. Good idea. Excellent. Good. So I have a few more minutes. So seismic data, or in general, these geological models have a lot of uncertainty. I mean, these models are completely uncertain in some sense if you just sketch from scratch. Yes. And I think this illustrative visualization can help to convey this uncertainty. And in a certain way it does, because it's sketched, right? If something is sketched, you know it's not so certain. But I feel still that when I look at your models, but this is all box. It still feels like, well, it is, but it does not show the uncertainty extremely well, despite that it's sketched. And I was just wondering if the sketching techniques do not be used by the geologists to also sketch the uncertainty in some sense, right? So that you have some way to kind of like blur the boundary of the river. It could have been here, or the thickness could be in this range, and so on. Because when you show the processes and the animations, then I guess maybe a geologist doesn't, but me as a computer scientist, I look at them. This is how it deformed, but of course it's not. It wasn't exactly like that. Do you have any idea how you could introduce more uncertainty in your visualizations, more than just that it's sketched?
Yeah, you're right. There are some techniques that works on the uncertainty, and in our case, we can convey this uncertainty just with the application of this color map into the model.
That's true.
Yeah, but you can play with colors and an legend, so where you are more sure of the process, or you have more uncertainty. But yes, you can also, as you said, you can also play with the uncertainty and sketches, even values. And there is a paper written by Ender, that is a quote of one of the papers, that plays with uncertainty when it tries to give more alternatives in the process. So one geologist can interpret one event in different ways, so he can sketch different alternatives of the same situation.
In principle, one could also certainly becomes more capable like this, yes. So that certainly. So, the next part, I think while it's not mentioned in your papers, I think your work could also inspire further research in the interfaces. Since sketching could be very well supported with pen-based or touch-based interfaces. When I think of sketching, I think of a pen. But a pen is not mentioned in your thesis nor in your talk. So I think there is the potential to improve the interface. I know you work very hard on the visualization techniques and the possibility to enable the sketching. Fine. But I think there's really the potential to go further and draw really with the pen these lines that form textures and so on. Have you thought about that or done some of that?
I used the pen in some of the examples I haven't mentioned it.
Okay.
For example, in the animation, we use the pen when we wrote the first configuration in the last. And I did it to just get the device. But for me, it was easier with mouse. I guess the mouse.
I see. But you haven't shown the pen-based interface to the geologists?
Maybe yes. For the paper, the paper 2, where we had this animation, we used the pen in the geology.
Okay, cool. You could have written that in the thesis because I think it's so now, since you invited me and my group is called Virtual Reality Systems, I of course have to say something about that these models are 3D, and you truly work with these models probably in 3D, and for example sketch on a model in 3D using, for example, a phantom device, a haptic input device. Maybe you don't have one here, but have you ever used the stereoscopic visualization? Have you ever seen your models in 3D?
No.
It's amazing. I think when you want to sketch on something that's really such a shape and it's in 3D, you could easily use a 3D pen and this force feedback device and just move along the surface and sketch on the surface. I think it would add a lot, extend your work nicely. But I guess it wasn't possible to use nevertheless. And I have to say that despite all their limitations, stereoscopic displays could also be considered to facilitate the process of building these spatial dimensional models and communicating complex geometric configuration. I think you build these complex models and communicating a model, you can spin it around or print it out or something like that, but looking at it in 3D, I think has some potential for your work. One last question. So, if you think you build these models, you did one more, maybe people start to stitch them together, larger and larger models, right? And you add more detail. So the question is really, how does your approach scale over larger models? Because in paper C, you're saying that you can deal with up to 50 layers in your current model, but in real time. So the question is, where are the limitations in the algorithm? Why is it only 50 layers of a certain resolution, 512 by 512 or something like that? And then how would you, what would you need to do to go beyond 50 layers and maybe even to very high resolution, 1000 by 1000, 2000 by 2000 grids and so on? Because I think people would use your software and use cases where they have larger terrains and they need to stitch together these different types of models. So how would you extend your work to support larger models?
Yeah, one limitation we had is the hardware limitation. So maybe you read it was 512 the grid, and then yes, then you multiply for the number of layers. Then we have already a lot of data. And it's true, it's really useful to have this larger scale models you can get. Maybe one limitation that is also given by the hardware is that you cannot have multi-scale details in the model. But in theory, it's possible to find something that is really small. Maybe you zoom out and then you sketch something else with more large scale.
So you mean manual level of detail,
Yeah.
kind of manual? I think your models could be also could also work for automatic level of detail generation, and then especially height fields can be nicely reduced in detail. And I think for a real geologist suit, it could be extended to use software. I think the number of layers is not the problem. The memory is at some point the problem, and the performance is probably the limitation currently because you use really regular volumetric sampling. And if you have a 1000 by 1000 model, you probably should have a sample rate that's appropriate. Uses 1000 steps. So I think there's potential to scale into larger models. You just need maybe different data structures to manage your height fields, your section height fields. Okay, I think my time is up. Thank you very much for the presentation and for the excellent discussion. And I look forward to more discussion afterwards.
I'd like to thank the first opponent, Professor Verdi. And now I have the honor to call upon the second opponent, research scientist André Brodko. Thank you for having the opportunity to come here and to be able to read this thesis, which has been a great pleasure. Now, the topic of this thesis has been on the sketching of geological features. That's sort of the essence here, and sketching. And as has been mentioned already, you have been very productive with the thesis being based on 3 papers, with 2 side papers and another 2 papers, so 7 papers in total. That's, I would say, very impressive in the 3 years and 2 months you have spent on this work. The thesis has been very well written, and it's been a joy to read it. And my role here is now to ask you some questions. And I have read through your thesis and sat with a very good impression, and some things I want to ask you a bit more about. You start off with the idea of sketching, and you neglect the possibility of using real-world data. Now, this has been a deliberate choice, but can you envision any way of incorporating real-world data, like seismic data or well logs, into your sketching framework?
Yeah, for example, with the seismic data, you can start sketching with the background, the seismic data, and then you are guided by the seismic, and you can see lines and shape of waves from the background. And this is one way. Or another way is to use maybe some state-of-the-art method that interpolates samples on film, and then you construct a model, and then you work on that, you sketch on that model to maybe to have more alternatives for scenarios on the plane. Those are the approaches that I have and think about.
Yeah, and I think it would be very good to enable such a use for geologists who are experienced in watching these
seismic data and the well logs and so on to be able to quickly sketch this up in a semi-realistic way. And that brings me to a related question, which is, these are sketches, right? And they are presented to the board of Statoil in your story, in your thesis, in which Statoil will decide how many millions of dollars they will spend on a project or not to go to this project. And then the question quickly comes up, how do you challenge such a sketch? Because if it's really distinct from the real world data, if you understand what I'm saying, it's still a sketch. How can this be well challenged by geologists to say that, is this a figment of imagination, or is this really what happened?
It's not really what happened. I think this is the interpretation done by, for example, geologists. And with the sketch, you can put the focus on the important things and on what you want to show to the others. So the sketch is it achieved its goal in a way that is relative to the ability to the user. I mean, the focus that the user puts on the meeting, it's basically based on him or her.
Yeah.
Then the sketch is just a medium to convey that.
Related to this, because I've seen this, and I came up with some ideas which I thought were fascinating for me, and maybe you can educate me on how realistic this will be. Because I've seen some geologists where they start with a model and they try to go back in time. They try, for finding oil, for example, you would try to find where would there be a lot of deposition of organic material, and how would this be trapped, and how would this move in geological time into today, which will lead us to an oil reservoir. And there I saw the coupling of perhaps some simulation and your framework, because you do have some simple simulation already implemented. The compaction, which is basically a very simple simulation of how the geological compaction process works. Would it be possible to incorporate more simulation techniques to your model to sort of sketch not only a single snapshot of today's situation, but perhaps a timeline of how things have progressed in time?
Yeah. For example, when I showed the animation of 2 layers folding, then in that case you can sketch the different frames that are called key frames, where you know, maybe not for sure, but you are almost certain that at that point there is this certain process. And then the animation can go back or backwards as well, so you get an impression of what happened going back in time. And yeah, otherwise you can also compare that with the approach described in the other 2 papers. You can define the initial configuration and the final configuration, and try to explain what's happening in between. Or for the fault, for example, for the fault process, in the user interface there is a slider where you choose movement on the fault, so you can show the process in time.
And often these geological processes are a sequence of events. First you have basically some deposition, and then you have some folding, and then you have some fracturing, etc. Does your framework support this, or is it just animation of a single folding? If you understand what I'm saying, like the history of first you start off with the initial constant layer thickness, and then you get the unfolding, then you get some more deposition, then you get a fault, and then you get future depositions and so on.
Yeah, this is also squadding. You can sketch and sequentially sketch each process, and then it will build on top of the previous one.
Mhm.
So you can have more processes in the same registration.
And this is, so you basically have a time slider where you can go back in time
Yeah.
and see everything.
Yeah.
So your temporal cut
Yes.
actually supports also the reverse of the compaction and so on.
Yeah.
Very good, because that was one thing I was hoping was there. Another thing that I think would be very relevant for this, of course we're in Norway where there is a lot of oil industry, is to try to simulate this with oil or organic material moving throughout its geology. Have you any thoughts on how that would be possible to do? Because this is sort of related to your fluvial systems and good reservoirs for where you have oil.
Yeah, we have thought about introducing layers that behaves in different ways. So you can maybe have a layer that represents some fluid, and this fluid goes to another layer because the other layer is impermeable, and then the fluid that wants to go up, then pass through. This is a further step we are looking for future work, because now it's not implemented.
Yeah.
Because it's completely different behavior. Because now the layers are considered as solid layers, so they deposit on top of each other, and there is no way to have one layer going to the other.
Yeah.
But it's definitely a good starting point for future work.
Do you think it would be easy or difficult to make this work in your setting?
It's not so easy, because the representation has grids or height maps.
Yes.
It's not well suited for fluid simulation.
Well, it may be, because there is a lot of simulation using these, or at least volumetric representations.
Mm-hmm.
But that brings me to another question, which is related to what was mentioned already, and that is the representation. Because you have these Cartesian grids with regularly spaced intervals, in this case 512 by 512 cells, and you stack each of these on top of each other. You have the limit of about 50 layers or so. Would it be possible to use another form of representation?
Yes, so, but we thought that this one was the one that it was the best representation to achieve the parallelization for each point of the grid and to implement it on each view. But for sure it's possible to use other representation. But maybe you lose some interactivity when you want it.
Maybe, but maybe you would also be able to support larger models, because I would say there's a lot of redundancy in a lot of your layers, because they are, in a broad sense, relatively smooth. Am I right?
Yeah.
So they're relatively smooth, and you could perhaps represent this in a more efficient way, and perhaps reconstruct only when you do visualization or so. Do you think that would be a way to go, or something like a spline representation for the different layers?
Yeah, it can work, and we have a list of information in the height maps, because a lot of points when you define, for example, the river, are set as 0.
Mm-hmm.
So you can also reduce this information, achieve more larger models.
Yeah. Have you looked into this at all, or is this still future work?
Just the thoughts.
Yeah. Okay. And let me continue now to your focus on non-photorealism, because your focus has been on the sketching part. And on some of your sketches, I see there is a difference between the manual illustration and the computer-generated image. Of course, there is a difference because the person has sat there drawing it, and the other has been just created. And I see that there might be a huge benefit for using certain additional effects on your images, such as drawing the contour lines, or as was mentioned already, adding textures to your 3D models. And this comes back to one of your aims, which is to impress the board of Statoil. Basically said that we'll go for this. Do you think that photorealistic effects have no place in this sketching framework at all? Or is it possible that there is room for adding certain effects?
I think there is, you are right, you can maybe for some parts introduce the photorealistic effect. And we did it in the first approach with the textures. And I think it's possible also to include it in the latest results. And but for let's say has to be supported by experts' wishes. So
Yeah.
If they drive us to this direction, then it's a good idea.
Yes, because I also enjoyed the part in your thesis where you actually have a user base which evaluate your work. Have you gotten a lot of feedback from the tests? That would be nice to have, also related to this new Illustrator project, right?
Yeah, and they said that if they prefer it in this way that is simple and maybe less photorealistic, and you can, as we said already earlier, you can keep the quality level compared to the abstraction of the illustration. So if the model is more abstract, then you have a certain level of abstraction or uncertainty in the model. And yeah, we had a lot of feedback from the experts, and the main feedback, the main limitation was on having more virtual events, because maybe
That is more layers.
Someone is more someone is more an expert on another topic in geology, so they want specific geological processes.
Mm.
And yeah, we try to give a general tool for having general models that can be most of them.
Okay, so let me try to change pace and ask you some more technical questions, and then I'll see if I come back to some more philosophical or similar type of questions later on. Now, the interactivity of your raycasting was lost at about 50 layers or so. Would you see it as possible to use other techniques than raycasting? Or is raycasting an essential part of what you want to emphasize here? Would something like ISO surfaces be equivalent for certain types of visualizations? Because I think for a lot of users, interactivity is key. If you cannot really interact with the model, you lose interest and you get frustrated with your work.
Yeah, about ISO surfaces, we talked about having representation. The problem is that you need at the point when you want to render, you need to convert our representation to ISO surfaces, for example. And there you use computational cost that reduce your interactivity. And recasting done directly on our application was the choice that led us to achieve the interactivity in the final end.
But still, there's a one-time cost, right? You do it every time you change your model, and then it's fixed. And then you can interact with your model. Whilst raycasting, you have to do every frame, every time you rotate your camera. So you still think it's not worth pursuing, looking at other types of visualization?
It's worth it. But, yeah, if you want to change the model, then you have to do another conversion. So if you look at the final model and you don't change it, then you can. And if you want to make changes or to add other scenarios, then maybe it's better to stay in that.
I think there should be room for both.
Yeah.
And I think it might be worth exploring for the cases in which you're unable to achieve interactivity. Now, you have implemented this on the GPU. What is your experience with GPU implementations? Is it easy to get started? What?
No, it's not easy to get started, but when you have all set, it's easy to write the algorithm that is necessary to make the rendering element. But the setting up it's not so easy.
Yeah. And this comes back to sort of the spectrum or the target audience of your tool. Because you require a GPU from NVIDIA, and perhaps also a quite powerful workstation to make this run interactively. Yet most meetings take place with simple laptops, or iPhone, or iPads, and similar. Do you see any limitations here, or how does the technology requirements of your algorithms and implementations steer the usability of this tool?
Yeah, my hardware is already 3 years old, so
Yes.
I guess now on the laptops from today you can find more or less the same graphics card.
Yeah.
And so it shouldn't be a problem to use it on a laptop or another PC. You can buy without any. It's not so expensive.
Have you tried running it on different machines?
Yes, the most powerful was the one I had in the office. So it's 3 years old now.
Yeah. And for this user survey, was that performed in your office? So the users would come to your office, show a video, or try the tool?
Yeah. It happened like this for more or less half of the participants, and then the other half was shown the video, tutorial video I had in the presentation.
Where did these experts come from? Were they part of the project, or?
Not everyone. There were students and postdocs, professors, but from different institutes, and from academic, from companies, different variety of people.
And they participated because they had an interest in this tool, or how did they get invited?
I was asked by a geologist, and he was inside the project.
Yes.
And then we also had some other contacts, and they were interested in seeing this tool, and also looking at feedback. So we're happy to see the tool in action.
Okay, so let me continue a bit with this code, and you've implemented with CUDA, etc. and OpenGL. Is that correct?
Yeah.
Yes. Do you require any specific version of OpenGL, or this should basically work with any?
Yeah.
Is the source code available, or is the software available for general use, or is it closed source?
No, at the moment it's not available.
Do you have had any discussion on making this more available to more participants, or is this perhaps closed in the funding?
Yeah, it's something that is dependent on the project, so I don't have the power to distribute the code.
Because I think a tool like this, because you compete with Adobe Illustrator, right, and you can do the work in 2 minutes versus a full day, or using your tool. And this would be a huge benefit for a lot of research community, and there's a huge community interested in the geological project. I think it would be a very good contribution to the world of knowledge to have such a tool open to more than one client, but of course that is outside of your hands. If we continue a bit with this implementation, what is the most time-consuming part of your algorithm? What takes the most time? Because you spend something like 2 minutes computing the image. What is it that takes time?
I remember well the most computational expensive part was when we converted the sketches to the height maps. That was not an optimized algorithm, so we can improve that one, and that took half of the time.
Mm-hmm.
But then for the rendering part and for the modeling part, it's quite good.
Okay.
I think the conversion from sketches to height maps was the most.
And which parts of your algorithm have you implemented on the GPU?
The rendering and part of the conversion.
Okay. Why not all of it? As it's the slowest part, other than those that you have moved over to the GPU.
Yeah, let's say one part is completely on GPU, but the other one I checked on the GPU, and it was almost the same time on the CPU. Mm-hmm. So I decided that it worked well because it didn't give me any crashes or bugs on the code. So it was same time and same efficiency. So I decided to keep it on.
How stable is your tool? As you mentioned, crashes and so on, because that's one thing that we all experience with software. Is it works well enough to create this video, or is it works well enough to give it to an engineer?
It works well enough to have the user study, let's say, with the user and me on the side, check that everything goes well.
Okay, so it's don't click this button right now, and because everything will crash.
Yeah.
Okay. But of course, it's a prototype, and I would say it's very impressive. The part you have moved over to the GPU, which is part of the conversion from your height maps into your full model for visualization and the array casting. Mm-hmm. Would you say that these are memory-bound or compute-bound algorithms, or what would you say is the limiting factor of, for example, the array casting? Have you looked into this?
The limitation for
the limitation. Why? Will the array casting algorithm be limited by number of computations you do, or the amount of memory you have to move back and forth?
I think it's also related to the memory. Because the computation, it's quite easy. The algorithm, it's very short.
Yep.
But the limitation is on the amount of samples.
Yeah, I completely agree with you. Have you looked into how to transfer memory on the GPU? Or have you basically followed an example? Or how much work have you done in this part?
Yeah, more or less I followed the samples,
Mhm.
and then yeah, my part was to write the algorithm. We used the 3D texture to move from the CPU to.
Yes, so you construct a 3D texture on the CPU and you move it to the GPU
Yeah.
and perform the ray tracing there. Have you looked into other sort of ray tracers, such as NVIDIA Optics, which might help you do this automatically?
Right.
Because I think that is one thing that you can do to also increase the visual impressiveness at a very low cost, as you're already using NVIDIA GPUs and you can use this framework. Now over to your user interface. It's clearly sketched, right? Especially for the arrows and so on. Have you thought about using gestures for some of your sketching? For example, I see in some of your sketches you have drawn arrows, right?
Mhm.
And you can clearly see that these are sort of hand drawn. Have you thought about using gestures for this? Also for like the compaction and for the faulting and so on.
Yeah, this is a good idea, but for example, for the arrows, I don't need to draw exactly the arrow. The arrow is just drawn for the as a notation in the panel. When I want to define displacement, the user has to just to draw the segment. So it's already a simple gesture defining the direction of the displacement and the amount. But it can be improved a lot with the other features, as you said, with compaction.
And I think if you're able to couple this with adding logos or sort of like stylized arrows in your sketches, that would be a good contribution to selling like your real sketch. Now you have 7 different papers. 2 of them are unrelated. How come you've worked with unrelated things in your PhD? No one else has done this, right?
Yeah, unrelated, yes. It was an extension of the work of the master thesis.
Yes.
So it was already in my background, so I didn't have to work out on the state of the art or something.
So you were able to leverage your previous work to get a couple of papers starting before you found your real subject and really focused on that.
Yeah.
I think it's very. Now I have one final question for you, and that is, if you got one more year with full funding, continuing with this project, what would you do?
I think I will work more on the, because now, as we said before, we are using 2.5 D. So it would be a good idea to work on improvement of to reach more complex shapes in the model. Like overhanging shapes that is not completely possible now, but it's with some tricks. Maybe in the first approach, not in the second one, because I cannot compare.
Yes.
Yeah, this is one of the way I would do.
Yes. So perhaps going to a different representation altogether, or
to mix the two.
mix different representations. Are there any further requests you've heard from users that would be interesting to pursue?
Now I don't remember. There was some specific features like improvements on the position of the deltas. Because now it's maybe it's too simple, but with a few more headings you can can achieve much better and more related to the real world event.
Yeah. Okay, thank you so much for your answers to my questions. I would like to thank the second opponent, research scientist Andre Ulfgård. Now it's my turn to ask questions, but not to the candidate, but to the members of the audience. Are there any questions or comments from the members of the audience? Helge Carlsen.
Thank you very much. I mean, this already has been a nice and long defense, so I will not ask all of my questions. I can do this later. But one that I find really important is when I look at 2D geological sketches, then I see a lot of annotations. So text annotations and other types of annotations. If I look at your 3D sketches, I see not none, but much less annotation. Is this because it's not possible to have a good solution in 3D for annotations, or how would you do it if you would have more time to implement it?
At the moment, it is possible, but it's just a translation from the 2D sketch on. It's a projection of the sketch on the 3D model. So you can have annotations.
But it may move out of view if you rotate it, right? For example. So I mean.
No, you can project it on the surface.
Yeah. Mm-hmm.
So when you move it, it's just it's still it's kept on the surface.
Yeah. And similarly, I thought that in a 2D sketch, I find it very easy to represent unknown pieces, right? You leave something blank, or you draw a big question mark over it, and thereby you make very clear. For this part, I have no interpretation. I mean, it could be anything. I better leave it blank. How can you leave something blank in your sketches in 3D?
Yeah, this is more related to the uncertainty visualization. You can introduce some uncertainty visualization into the model and have this, instead of having question marks, to have different visualization into the 3D model.
Mm-hmm. Yeah.
Yes.
Yeah, I was wondering, have you thought about bringing more quantitative information to the final model? Because many things are easy to compute. For example, volume areas of different layers. Because since you have anyway the grid and you have a height field, it's a summation. Do you think that this could be helpful for the end users to see such information there?
Yeah, it is helpful to see it maybe in background or as a transparency point. But it's yeah, you have to do it constructing the model based on that. So the intuitiveness or you cannot build the model as you want. You have to be constrained on that point that you get the measurements. So it's not more visual thinking from the user.
But I more meant like a guidance. For example, on the right side of the model there will be some bars displaying some volume areas, for example, layers or some other info.
Yeah, you can have geometric constraints or other constraints. But it's of course it's not implemented now, but it's doable.
Yeah.
Yes.
But you, in the course of the discussion and the questions and your answers, already some statements were made about the requirements in terms of technology for your solution. If I had the idea to specify a student project, take Matthias' work and implement it on the iPad, would you recommend me to give such a project to a student or not?
Maybe not on.
Maybe not on the iPad?
Yeah.
Yeah. But on a laptop, I mean, that's what you said, I heard. On a laptop, yes, but not on an iPad.
Yeah, it's not so easy also on a laptop. but maybe a small part of it can be assigned to a student.
Because I know we have discussed this in the context of the project, that our collaborators from geology, they are out in the field, and they have to do their studies there, and they have their notebooks where they sketch what they see, right? So I just thought that, like, picking an iPad, taking a photo of what I'm seeing and converting it within 2 minutes into a 3D sketch, that would be great.
Yeah, but the limitation, I think, is more on the art.
Yeah.
Because with a picture you can still use some algorithms taking contours. And then from that you go back into this approach. And then you have the 3D model, but the limitation is on the art. Yes.
Is, I mean, this recommendation of the hypothesis because of the lack of purchase power, or because of the internet?
No, because of the graphics.
So maybe with a remote modeling, like let's say you do this heavy work on some server.
I guess in this way it's possible. You use the power in the cell on the server, and then remotely on the light.
The committee will now leave the room to discuss and evaluate the defense of the thesis. I'm asking the audience to stand up while they're leaving. But after the committee has left the room, the audience are kindly asked to remain seated while waiting for the committee to return and announce its decision. We will return in a few minutes.
You can do it now or then afterwards. When they come in, then you should not. When they come back, then you should not. Okay. Starting to relax.
Please be seated. This is the serious part. The committee has now evaluated the performance of the candidate, and I'm happy to conclude that the committee has accepted both the presentation and the defense, and will thus recommend that Mattia Nathalie should be awarded the degree of Philosophia Doctor at the University of Bergen. The university board will be notified accordingly. The formal disputation has now come to an end, and the candidate may have the floor.
Thank you very much. And first of all, I want to thank my supervisor, Daniel, that this year has been to achieve such a result. And then Ivan, that today is not here, Viola, is now following us, see on streaming. And thanks also to Elvik, that helped me in different ways, also relaxed me before the defense today. And thank you very much to all of you that came to speak. And thanks, of course, to the committee.
entire ceremony has now come to an end, and while the audience is again standing up, the procession that entered the room at the very beginning will now leave. But as a tribute to the doctoral candidate's new status, I'm asking the candidate to leave the procession.
Yes.
Someone check if you have any questions.
Yeah.
It's under 2 minutes or 3 minutes.
Ah, okay.
Somebody switch off for the sound.